Okay, so what does all this have to do with rotation matrices? Let's answer that question. Okay, so back to rotations. Okay, so here I'm going to ask another question. Okay, so here's a question. So suppose I have some arbitrary vector. Okay, it's a unit vector. Let's call it omega hat. Okay. Now what I want to do is I want to rotate some vector, say that vector, around this axis, omega hat, by some angle. Okay. So let's call this vector, say, p sub 0. Okay. And let's rotate this vector p sub 0 around this axis by some angle, theta. So okay. So it rotates to this vector, p sub theta. Okay, so this angle here is theta. Okay. Now, what I want is I want an explicit formula for p sub theta. Okay. So rotate P0 about omega hat axis, okay, by angle theta. Okay, and this gives us p theta. All right. So what I want is an explicit formula for this. Okay, so formula, what is it? Okay, so this is how we're going to get to rotation matrices. All right. So the way we're going to get here, okay, is maybe a little bit unconventional. There are different ways to get here. Okay, the way we're going to go is we're going to formulate this as a differential equation. Okay, and use what we learned about linear differential equations. Okay, to derive the solution. Okay, all right. So here's what we're going to do. So let me redraw that picture again. So omega hat. Okay, what we're going to now do is we're going to imagine that this vector p of p0 rotates around this axis at some uniform speed. Okay, let's say it rotates at 1 radian per second. Okay, so imagine p0 rotates at 1 radian per second. Okay? All right, so it's rotating. So it's going to trace a circular path. Okay, so it's going to trace a circular path. Okay, so so here's p sub theta, where we want to get to. And okay, so let's call this path p of t. Okay, let's path traced by this vector p0 as it rotates around omega hat. We're going to call that path p of t. Okay, so after 1 second, how much has it rotated? 1 radian. After 2 seconds, it's rotated 2 radians. After t seconds, it's rotated t radians. Okay, so in fact here, t is the same as theta. Okay, so t is in fact just theta. Okay. All right, so here's p of t. It's tracing a path p of t like this, a circular path. Now let's ask the question, what's the velocity? Okay, what's the velocity of this, imagine this particle, okay, moving along the circular path. The velocity, let's draw it. The velocity is going to be always tangent to the path. Okay. So here's p dot of t. Okay. Right? As it's tracing a circular path, the velocity is always tangent to the circle. Okay. All right. So in fact, it's not too hard to see that the velocity can be written as a cross product. Okay. So the velocity p dot, in fact, is equal to, let's see, well, the direction is always tangent. It's going to be omega hat cross p. Okay, so you can verify this. So you know how to take cross products using your right hand. Right, so omega hat cross p gives you the direction. The thumb indicates the direction. Always tangent to the path, as required. Okay, and the magnitude, right, we know is the magnitude of omega hat times the magnitude of p. Okay, so here, okay, so omega hat is a unit vector. Okay, so let's remember that. Okay, so the magnitude of p dot is the magnitude of omega hat, which is 1, times the magnitude of p, times the sine of the angle between omega hat and p. Okay, and so you can convince yourself without too much difficulty that in fact velocity is given by omega hat cross p. Okay, all right. All right, so now we're going to do something that might seem a little crazy. Okay, we're going to write the cross product in some strange way. Okay, so here's what I'm going to do. All right, so let me introduce a bit of notation. So if I have some vector, say v, three-dimensional vector, okay, I'm going to use this notation, v inside square brackets, okay, to denote this 3 by 3 matrix. Okay, it's going to have zeros on the diagonals. Okay, and in the off-diagonal terms, I'm going to arrange v in this fashion: minus v3 here, plus v2 here, minus v1 here. Okay, over here I'm going to switch the signs. So here I'm going to put plus v3, minus v2, and plus v1. Okay. Okay, so why am I defining such a strange matrix? Well, before I get to that, this has a name. Notice that it's not quite symmetric. I mean, the diagonals are 0, and these are mirror images of each other with respect to the diagonal, but with the signs switched. Okay, so a minus here is a plus here is a minus here is a plus here. Okay, so these matrices are called not symmetric matrices, but skew symmetric matrices. So skew symmetric. Okay. All right. So anytime you see a three-dimensional vector written inside square brackets like this is what I mean. Okay. All right. So the reason for introducing this notation is that I now want to write the cross product as a matrix times some vector. Okay, so here's a proposition. So if I have two vectors given u and v, okay, two three-dimensional vectors, okay, the cross product of u and v going to write as the matrix U, okay, obtained as a skew symmetric representation of this vector U times V. Okay. All right. So pretty easy to check. Okay. You can probably just do it in 10 seconds now if you want, or you can just take my word for it. But trust me, this works. Okay. So we're going to write cross products in this strange way. Okay. You say, what's the point? Okay. Well, let me get to that in 1 second. I'm going to write one more formula here. So I have U cross V. If I now want to take the result of U cross V and arrange it in this skew symmetric form, another way to do that is just to take UV, the skew symmetric representations, minus V times U. Okay. All right. So these formulas you can all just check by calculation. Very easy. Okay, so now I'm going to write that equation. P dot equals omega cross P in the form P dot equals the skew symmetric matrix omega hat times P. Okay. All right. So now if you have the matrix, the equation in this form, now we can use the tools that we developed earlier, okay, to find the solution. Okay. This is of the form what, x dot equals ax. Okay. Okay. So really doing a lot of just sort of crazy stuff, right? Writing cross product in this way, writing things as a differential equation, okay, just to figure out what is P of theta. Okay, but since we're down this path, let's continue. Okay, so here's our equation. All right, so I know most of you probably like to travel, right? So what's the point of traveling? The point of traveling is not to get that picture in front of the pyramid or the Eiffel Tower, right? What's the point? The point of traveling is the process itself, right? That's the real fun of traveling, right? Getting there, right? Missing the train, right? Getting lost. Okay, that's the process. So education is the same way, kind of. Okay, it's not the end result, the end formula, but in some ways it's the process. Okay, so the end result. Okay, I don't want to say it's not important. Okay, the formula P theta is important, but the process that we're going through. Okay, that's just as important here. Okay, so it seems like we're sort of taking. So it looks like we're getting lost, right? But we're gonna get to our destination. Okay. But this process is kind of, I think it's meaningful, okay? All right, so there we have it. So remembering, okay, that what we assume that the rotation occurs at 1 radian per second, which implies that t and theta are the same. Okay. So remembering that t is the same as theta, okay, we're going to write the solution. P of t is equal to what? Exponential omega t p0. Okay, we're going to write this. Now let's just get rid of, replace t by theta. Okay, so let's work with this now to sort of remind us that what we really want is this formula for P of theta. Okay, angle theta. Okay, I think I can erase this. All right, so let's find this. It's not diagonal. Okay, so we're out of luck there. Let's see, can we diagonalize this matrix? Well, it seems like it's a lot of work. It requires some work. Okay, so let's just try write down the definition. Okay, maybe some insight will occur to us. Okay, so this, remember, is I plus omega hat theta plus omega squared, theta squared over 2 factorial. Okay, plus, let's write down a few more terms. Omega cubed, theta cubed over 3 factorial. All right, why not? Let's write one more. Oh, there's some space here. Let's write one more. Okay. Okay, so there it is. Let's see. Is there some result that we haven't used that we learned last time? In fact, it just occurred to me that I forgot to write down Cayley-Hamilton theorem. Okay, so let me do that for you now. Okay, this. Okay, so now let's recall Cayley-Hamilton. Okay, and this theorem says that if we have some matrix A, n by n, okay, then its characteristic polynomial, P sub s, okay, is the determinant of is minus a. Okay, so this is going to be some polynomial of degree n. Okay, it's going to be s to the n plus c n minus 1 s n minus 1 plus dot 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 plus s 0. Okay, Cayley-Hamilton then says that P of a. Okay, so if I replace s by a in this formula, in other words, we get a to the n plus dot 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 plus a1 times, a times c1 a plus c0. And we can't add a scalar to a matrix, so there's an I here. Okay? Cayley-Hamilton theorem says that this is 0, always, for any A, guaranteed. Okay? All right, so let's use this. Let's use this. Okay? Let's use it and kind of hope something comes out. All right? So now let's find the characteristic polynomial for this. Okay, so determinant of is minus omega hat. Okay, this is going to look like determinant of, let's see, we have s's on the diagonals. Okay, I times s. Now we subtract omega hat, skew symmetric matrix. So we'll have a omega 3 here, minus omega 2 here, and a plus omega 1 here. And over here we'll have minus omega 3, plus omega 2, minus omega 1. Okay, so this is the matrix whose determinant we want to evaluate. Okay, and now we have a formula for calculating the determinant of 3 by 3 matrices, right? What do? We take the cross product of this and this, okay? And then take the inner product of that with the first column. Okay, so I'm not going to do the calculation now. It's easy enough. Turns out this is going to be s cubed, okay, plus omega 1 square plus omega 2 square plus omega 3 square times s. Okay, but we know that this is a unit vector. Okay, this is a unit vector. So this is just s cubed plus s. Okay. All right, so now if we apply the Cayley-Hamilton theorem, then we know that replace s by omega. So omega cubed plus omega is 0, or minus omega cubed is minus omega. Okay, and this follows from Cayley-Hamilton, just described. All right. Let's see if this helps us. Okay, so let's go back here. So I see omega cubed here. I can replace this by minus omega. Okay, see an omega to the 4th. So this is omega cubed times omega, or minus omega squared. Okay. Now I see an omega to the 5th here. That's going to be minus omega cubed, which is just plus omega. Okay. And so we can keep playing this, substituting in this fashion. Okay. Do it for all the terms. Okay. So what we end up with is the following. So e to the omega theta is equal to, we have I, plus, so we have a term involving omega, the skew symmetric matrix, and another term involving omega squared. Okay, so collect all the terms, okay, for omega, put them in here, the scalar coefficients, collect all the terms for omega squared, add them up and put them in here. Okay. So what we'll get is we have a theta here. Okay. And then the next omega is minus theta cubed over 3 factorial. Next term is plus theta to the 5th over 5 factorial minus dot, dot, dot. Okay. Over here we have, let's see, for the first omega squared term, it's theta squared over 2 factorial. Okay. Next omega squared term is minus theta to the 4th over 4 factorial plus theta to the 6th over 6 factorial minus dot, dot, dot. Okay. So it's a little bit of progress. Now this looks familiar. This looks familiar. Okay. All right. Now if I ask this, if I show this to a second-year high school student preparing for college entrance exams, okay, they usually give me the answer in like 5 milliseconds, right? It's in this too. So, but now when I ask juniors and seniors, they, it's kind of fuzzy, right? Because college entrance exams are over, okay? But you remember, it kind of looks like a sine or a cosine or something, right? Okay. Turns out this is a sine. It's almost a cosine, okay? But there's a 1 missing. And it's a minus cosine. So it's a 1 minus cosine. Okay. All right, see? So I told you it's kind of fuzzy. Okay, so turns out it's equal to I plus sine theta times omega plus 1 minus cosine theta times omega hat squared. Okay, finally, there's our formula. Here it is. Okay, so let's write it. E to the omega theta is that. Okay, so there's our formula. And it's such a nice formula that we're going to put a, all right, there you go, like that. Okay, so we're going to give it a thumbs up. Kind of a strange thumb here. There we go. Okay. So, you know, a few years ago, like 10, 20 years ago, you usually draw a heart with an arrow through it to indicate that, this is a real sweetheart of a formula. But these days, I think this means more to right, today's generation.